Well, good morning. So I hope everyone is connected. My name is Jiří Drahoš. I'm president of the Czech Society of Chemical Engineering, and I'd like to welcome all of you at the today's seminar in the series organized jointly by CHISA Congress team, by the Gruyter Publishing House, and by European Federation of Chemical Engineering. I have to stress that this is already a third seminar in series, and main aim of this activity is the promotion of the European chemical engineering science under current difficult situation. Let me just to mention that first seminar was organized on 3rd September last year. Topic was process intensification, and speakers were two distinguished Dutch colleagues, Jan Harmsen and Maarten Verkerk. Second seminar was organized on 26th of November last year with the topic Teaching Electrochemical Energy Storage to Engineers. Speaker was Professor Reinhard Job from Germany. And I'm very pleased to welcome today Professors Riccardo Tesser and Vincenzo Russo from University of Naples from Italy at the third web seminar with the title Advanced Reactor Modeling with Matlab. Ladies and gentlemen, I have already mentioned the role of CHISA team of the Czech Society of Chemical Engineering, which will organize the CHISA virtually conference in about 2 months from now. The date is March 15 to 18. And for more information, please have a look. Yes, thanks to Ines for showing us the picture. You can see Virtual Congress Hotel is on your screen, and as you might have noticed, there is just a couple of people at the hotel entrance. Let me therefore cordially invite all of you to join them and to attend the conference CHISA virtually. Although the registration deadline for oral contributions expired a few days ago, but on January 15, we still have slots open for you. And moreover, deadline for posters is February 15. So we are very much looking forward to welcome you in Prague in March, though only virtually. Thank you very much, and I give my word to Karin Sora from the Gruyter company to say a few words, and then I'm looking very much forward to listen to the advanced reactor modeling with Matlab.
Good morning, a warm welcome also from my side. I'm Karin Sora. I'm Vice President, Science, Technology, Engineering, Mathematics at the Gruyter in Berlin for the German-speaking markets. And by training, I am a chemical engineer. And I spent 30 years in publishing, 17 with Wiley VCH Wiley, and 3 with Springer, and now 10 years with the Gruyter, building an international publishing program. And if you ask yourself, what is the Gruyter doing on this webinar? Well, we are very much endorsing these webinars with the aid of our authors. And of course, we would also like to raise awareness. So if you have content to publish, if you are thinking of doing a book, please also consider us in this process. So I will give you a brief introduction and then leave you to the actual talk. So okay, the Gruyter is an independent scholarly publisher founded 270 years ago. We have offices in Berlin, Basel, Boston, Munich, Beijing, Warsaw, and Vienna. Over 350 employees. We publish 1,600 books every year, also 800 journals. And we have over 20 international partnerships, which means that, for instance, Harvard University Press or Princeton University Press are distributing their ebooks via our platform. And we are also one of the largest open access publishers worldwide. So what does science, technology, and engineering and mathematics at the Gruyter entail? We publish in mathematics, We publish in technology, which is computer sciences and engineering. And here engineering would be electrical engineering and mechanical engineering. And then probably more interesting to this target group, to this audience, would be in the physical sciences. We publish in chemistry, in industrial chemistry, in chemical engineering, in material sciences, and in physics. And who are the people behind? You see Christine Smith. She will join the webinar a bit later. She's the acquisition editor. She's a chemist, and myself. And you see us represented at the Frankfurt Book Fair. So we have a very prominent booth there. We are a quality publisher. Why would one publish with us? Because we are fast, we are a quality publisher, and the authors are important to us. We have a wide range of books and journals published in different models. And how would this process go? So you would discuss the idea with either Christine or me, submit a book proposal. We will provide you with a template, and then one can write 150 to 350 pages, and the outcome is a beautiful book. As you see at the left-hand side, top of the page is the book fresh published by the authors of this webinar. It's Advanced Reactor Modeling with Matlab. Throughout the whole process, from the very first idea through research, writing, manuscript submission, reviewing process, publication, and even afterwards, we will support you. So we will be at your side in the whole process, because you as the authors are important to us. We publish in different models. We publish in open access. Now here we need funding, but if funding is here, then we can provide open access for everybody who is interested in your content. We also publish in the hybrid models, meaning that only the articles which have funding are open, and the traditional subscription-based model, which requires institutional subscriptions or individual purchase. Aside from the beautiful books, we also have a beautiful journal portfolio. And here I would point out to the audience of this webinar, the reviews in chemical engineering, for instance, which has an impact factor of 5.3, or the Journal of the Union of Pure and Applied Chemistry. We are their publisher. And these are the subscription-based journals, but we also have a portfolio in open access. And here I would stress out the green processing and synthesis at the top of the page, which might be interesting for this audience, or nanophotonics with an impact factor over 7. And with this, I would like to close and invite you to publish with us, and hand over to my colleague, Christine Smith, who will do the introductions of the lecturers. I wish you an interesting webinar.
Thanks so much, Karen, for that great introduction to the Gruyter. And now, I guess, to the authors and speakers today, Professor Riccardo Tesser and Professor Vincenzo Russo. So before I get into their introduction, I just want to give some housekeeping. During the webinar, you can submit questions in the Q&A section at the bottom of your screen. At the end of the webinar, I'll have previously gone through the questions and give them to the two speakers so that they can answer them. Okay, let's get into it then. So Professor Riccardo Tesser received his master's degree in industrial chemistry at the University of Naples, Federico II in 1989. From 1991 to 2000, he worked at Montefibre Research Center of Axial, researching DMT production and batch and continuous PET polymerization. In March 2000, he left industry and became an assistant professor in industrial chemistry at his alma mater, the University of Naples, Federico II, where he was later promoted to associate professor in 2014. His main field of research is industrial chemistry, especially industrial catalysis and kinetic studies of complex reactions in multi-phase reactors and related mathematical modeling, of which you will hear about today. More recently, his main field of activity has been in biofuel production and the use of renewable resources as raw materials for the chemical industry. He has taught MATLAB in basic and advanced courses for over 10 years. Professor Vincenzo Russo received his doctorate in chemical sciences at the University of Naples, Frederico II, in 2014. In 2017, he received his second doctorate in chemical engineering at the Abo Academy in Finland. Following this, he began as an assistant professor in the tenure track at his alma mater, the University of Naples, Frederico II, in industrial chemistry. Since 2019, he is also a docent at his other alma mater, Abo Academy, in kinetics and transport phenomena in chemical reaction engineering. His research focuses on bridging the fundamentals of molecular phenomena with modern concepts of chemical reactor engineering, with the aim to optimize and intensify chemical plants. So with that, I will hand it over to our two speakers. And yeah, very much looking forward to the presentation. Thank you so much.
Thank you, Christine, for the kind introduction. The first slide, this first slide contains our main information about our book, and obviously the price and the page and the QR code for accessing directly to the website. Well, the title of our presentation is a Matlab-based approach to chemical reaction engineering problem. And the aim of our presentation is to describe mainly the content of our book and to illustrate the potentiality of the code presented inside the book. This is the front cover of the book, the title, Advanced Reactor Modeling with Matlab, and some information about us. And in this occasion, I wish to, first of all, to thank our student, our PhD student, Carmelina Rossano, for the very nice artwork picture of the front cover that you can see here. And I will start with describe to you the content of the book. The organization of the book is made of 9 chapters. These chapters, each of these chapters are related to one topic, one topic, very well-known topic in chemical reaction engineering and modeling. The first chapter is dedicated to an introduction of chemical reactors modeling and contain some basic informations. The structure of the successive chapters are reported here, and you can see that chapter 2 and chapter 3 are related to batch reactors, discontinuous batch reactor. One chapter is dedicated to the homogeneous catalysis, while the other one is dedicated to heterogeneous catalysis, as in this case, particular, very specific problem have been faced, mainly regarding the internal diffusion and modeling of single catalytic particle. Then we have chapter 4, in which an ideal single-phase continuous reactor, also dedicated to the homogeneous catalysis in comparison, in parallel to what have been done in chapter 2, but in this case for continuous reactors such as plug flow reactors or similar, but in ideal condition and with a single phase. Then we have a chapter dedicated to real reactors for heterogeneous catalysis, in which we present some examples, some solved examples of reactor in which we have determined, we have described the residence time distribution and some techniques dedicated to this problem. The next chapter, chapter 6, is fully dedicated to packet bed reactor, continuous packet bed reactors. That is one of the main topic, and let me say the most difficult topic of chemical reaction engineering. The remaining chapters are devoted to some topics that are auxiliary, let me say, to chemical reaction engineering. That is, chapter 7 is for parameter estimation, and chapter 8 is dedicated to some statistical tools applied to chemical processes, mainly tools devoted to reactor optimization. Obviously, chapter 7 is in our opinion, is very useful for laboratory studies, but also in some cases for industrial applications. The final chapter of the book probably is the longest. Contains some case studies of chemical reaction engineering. I mean that in this chapter are reported the application of and the implementation of many of the codes presented in the first 6 chapters of our book. So this is the main content, a brief description of the main content of the book that you can find. Well, some general consideration about the chemical reaction modeling that I think is very well known to all the audience of this webinar. Well, chemical reactor modeling is a very specific sector of the broad chemical engineering science. But as the types of reactor is very large, we in some cases can be difficult to rationalize the modeling. So we have adopted the strategy to organize our modeling approach as can be organized the types of chemical reactors. I mean that the modeling follow the classification of reactors itself. And then we have developed the specific code for batch or semi-batch reactors, continuous stirred tank reactor, continuous tubular reactor, and this is a very wide topic, as we can see here, because include plug flow, laminar flow, or other some non-ideal flow of reactor, and also packet bed and trickle bed and so on. But this classification involve different strategy of modeling, and particularly the choice of different solver in Matlab. So we have organized our approach following the classification of chemical reactors. The modeling in our opinion can be set up with 4 different building blocks. These building blocks reflect the equation and can be easily transferred in function in Matlab piece of code. The first block is the basic block and is regarded the reaction mechanism, in some cases power law, or in many cases the more complex rate equation. The second block is the second piece of modeling is the mass transfer, the problem of mass transfer, in which we can account for convection, accumulation, or obviously chemical reaction, and molecular diffusion. This part of the modeling result in an equation like the one reported here, and each component in principle can have an equation similar to that. Then we can include in modeling, if the system is not in isothermal condition, an equation for heat transfer. And also in this case, the equation for heat transfer can account for different contribution. For example, for accumulation of heat, for heat transfer by convection or conduction, and for the reaction evolved or absorbed by the chemical reaction itself. And the other effect, obviously, if you want to improve, to implement your model. Finally, not even included in the usual modeling strategy, an equation for momentum transfer. That is an equation, a differential equation, partial differential equation that can account for different pressure between different parts of your system, different viscosity, and so on, phenomena of this type. So you can have a modeling approach that can be used that can use building block similar to that presented here. And each of these blocks can be transferred in MATLAB code and in particular in the specific functions or solver. Now we arrived at the main question in this presentation, I think. Why we have adopted MATLAB. We started in this decision by examining the problem. The problem is the chemical reaction engineering problem, a general problem in which the number of phenomena, physical or chemical phenomena that be considered in modeling depend on the user's sensibility and also on the user's necessity. For example, when you have to simulate or describe an industrial scale reactor, you need to keep into account for temperature and the concentration gradients along radius or along reactor axis, for example. So the problem can become very complex. And for facing this problem, we have to choose a tool. In the perspective of the market, many tools are available, many languages are available for solving this type of problem. But among these tools, we choose MATLAB because, first of all, because it's considered as the state-of-the-art package or language for scientific computations. But also because MATLAB, rather than a language, can be considered as an integrated environment, because inside MATLAB, particularly in this recent version of MATLAB, you can do coding, that is the main activity, but you can do also visualization of your results. And all this activity, data analysis, coding, and visualization can be developed, they can be done in the same framework. This language this language, but now has become an integrated environment, is constantly updated each year. I think about two times per year, a new version of MATLAB appears on the market. And today is a very huge collection of built-in function already tested, and a huge collection of mainly of algorithms, very robust. And with this function, the scientist, the user, can solve many tasks, many common tasks, with a single instruction in many cases, or with a single function call. This means that your MATLAB code can become very short and very compact, as we have developed in our book. Some other word about MATLAB. MATLAB has other characteristics that can be very useful. For example, the possibility to be interfaced with other packages. For example, as a strict interface with Excel, with console, and also with some data acquisition package like LabVIEW. And so the user can develop very complicated, very complex architecture in scientific computing. In MATLAB, the user have the availability of a huge number of books to learn MATLAB, and as you can see here, here there is a distribution of MATLAB book by areas of interest. In many areas, there are many books. Mainly, the main area obviously is mathematics, signal processing, or control system. And coming to our main interest, also in chemical engineering, the number of books is not negligible, as we have some around 60 or 70 books. But many of these books, and this is the main motivation of our book, in these chemical reaction engineering books, the topic, in this chemical engineering book, the topic of chemical reaction engineering normally is treated very shortly, in very few pages. And the example presented there are very easy, so not very interesting from an advanced point of view. How now let's me say some word about how we have organized in detail our codes, our examples. The approach adopted in this book, in our book, is to treat the chemical system in general way, without referring to a specific chemical molecules. So the chemical molecules are labeled in abstract form, like this reported here. For example, A plus B that give C plus D, without specify what is A, B, C, and D. And in our opinion, the main advantage of this approach is the possibility for the user to have a general code independent from specific chemical system with specific physical properties, and starting from this prototype of code, the user can develop its own code according to its necessity. Well, the example, as we can see in the table reported here, the examples are organized according to the type of reactor, as we have as we have said before. According to the reactor type, we can have a problem of simulate the reactor, or to estimate some parameter, some adjusting parameter in the model. So each type of reactor, for example, batch, we can have a simulation task or parameter estimation task. And according to this necessity, different necessity, we use MATLAB solver, different MATLAB solver. For example, for the simulation of batch or fed batch reactor, we have the possibility to use a solver for ordinary differential equation like ODE45, for example. On the other way, if we have the needs of parameter estimation, we can use a general minimization algorithm available in MATLAB that is LSQ nonlinear. The same approach can be used for the other type of chemical reactors. with the peculiarity that, for example, in CSTR, the user can have the needs to simulate the reactor in steady state of dynamic condition. And in this case, the choice of the solver is quite straightforward, because if you have to solve a steady state simulation problem, very, very likely you need an algebraic equation solver like F0 or FSolve. All these example, the combination of these type of reactor, task, and MATLAB function are included in the example of the book. Now, after this introduction about the structure and the strategy adopted in the book, we have chosen 5 examples of application, both of codes in the book and some, in particular for the example 3, of some application not reported in the book, but used as a perspective of what the user can develop, starting from the code reported. The first 3 examples will be illustrated by Professor Russo, and the last 2 by me. Now I leave the talk to Vincenzo.
Thank you.
That have an English very
No.
very better than mine.
Well, thank you again for all the organizers of this seminar to have introduced us and give us the opportunity to give this talk, to introduce our book. Thank you to the Gruyter for the big help during the production stage and in the publishing stage. Also, this is a story that started in CHISA. So this seminar is also, you know, very well framed within the presentation of this book, as the first contacts were taken by Professor Tesser and Karin in CHISA 2017, I remember. I helped to organize the example. Well, the structure of the book is such that the examples follow in a STEM area. So we are not talking about a MATLAB book devoted to, let's say, as a user guide for beginners. And this is not a book for people who want to learn chemical reaction engineering total. It is a kind of a further step. So the audience of this book should be already very well educated in both MATLAB coding and chemical reaction engineering theory. Yeah, one idea would have been, for example, to introduce something very deeply about the coding in general, the structure of the software, but there are a lot of books dedicated to that. And as Professor Tesser said, our main focus was to actually illustrate some cases that can be useful both for the academic world and industry to simulate more or less more complex cases. So real reactors where the fluid dynamics is not ideal at all, and so on. So that's why we started from a further problem. So this is not really a book that should be suggested for students who are just starting within the approach of coding with MATLAB or within the approach of chemical reaction engineering. So at least the theory should be known. As I will show you within the first example, we have decided to talk about the modeling of an heterogeneous catalyst particle. So we are talking about a single particle. So the mathematics that is behind it, it is not easily numerically solved by, you know, classically solved by handmade, but you should apply a numerical solver, because the mass balance for a spherical particle, so a reactant or a product diffusing within a spherical particle and then reacting, it's the one reported in the slide. So for an isothermal case, we have, of course, an accumulation term. If we are talking about a dynamic case in a continuous reactor, or the classical accumulation term for batch reactor, then we have a diffusion within the particle, here written in dimensionless form, and then generation 1. So having a look at that, we can see that the system is a partial differential equation. So I'm talking about a system because, of course, we should have at least a couple of components, chemical components, that can be one reactant and one product or whatsoever. There are a lot of solvers with which you can solve it, but as we are focusing about the use of MATLAB, we suggested use of pdepe, that is a very practical solver, not extremely general. It has its limits, but at least for single particles, or as we will see later, for axial dispersion reactors, or also laminar flow cases, like it is reported in our book, it is rather practical, because if the user gets in the way the equation should be written, then the solver is very fast executing, and you can get reliable results in seconds. So this is actually a case reported in the book. So I've also reported a table with the main parameters that must be fixed, and the reaction rate is just a classical first order reaction. Well, about pdepe, just a few words. It is a solver that solves initial boundary values problems for parabolic or elliptic PDEs in one dimension. So we have time and we have another dimension. So you cannot, for example, use this kind of solver if we have more than two variables, more than two coordinates. You have time and you have the reactor radius, then you can use it. You have time and you have the reactor axis, you can use it. But if you are, for example, trying to solve a combination of them, so time plus the axis of the reactor and the radius of the reactor, you cannot use that. So you have to choose another option. The syntax is rather, it's rather simple, because we have a solution at the left-hand side of the solver call. The solution, actually, it is a matrix that contains the variable of, in this case, concentration, calculated along time, and the particle dimensionless radius. Then we have the name of the solver, pdepe, and then we have several inputs. All of them, they are mandatory. You have to specify them. You have an index M that is related to geometry of the system, 0 for the slab, 1 for cylinder, 2 for the sphere. Then you have to define 3 functions. The first one, pdepefun, where the partial differential equation system is defined. Then we have icfun, that is the function where initial conditions are defined. bcfun, boundary condition must be defined within that. And then finally we have xmesh and tspan. The first one, it is the space grid. So we're talking about a vector where you want the solution along. So you have to specify the points where you want the solution along the dimensionless particle radius, and then tspan, that is the, okay, it is written integration interval, but more strictly, it is the interval and the specific time where you want the solutions. In the end, you have an optional call that you can also skip it, that is options, that is needed to tune up the calculations. You can use ODESET to specify the tolerance of the software, of the solver, or whatsoever. So this is the main syntax. Then, of course, MATLAB developers made a very nice work and to generalize an equation that you can see here. So you have to write down your mass balance equation, or heat balance, in our case just mass balance, in the form that that is very suitable for MATLAB syntax. You can see that you have to define at least three components, 3 terms. The first one is C, that can be a function of X, that is the position within the catalyst pellet radius. That can be a function of the time, of U, that is actually concentration in our case, and the first derivative of concentration along X. And this C is multiplied by the derivative of U with time. Then you need to specify M, but I've already talked about that, so we will skip that. And then you need to specify F, that is a second function that can be a function of X, time, concentration, and the first derivative of concentration. And finally, we have a term that can be either algebraic or it can be a first derivative, and also in this case a function of X, T, U, or the first derivative of U, that is again concentration along X. So we have high flexibility, but in order to solve our system, we have to take our mass balance, that is the one reported in the second equation at the left-hand side, and then to modify it in order to be, let's say, symmetrical compared to the MATLAB syntax one. But that's rather easy and straightforward in this case, because we can see that the time derivative concentration is just multiplied by epsilon. That means that C is equal to epsilon. M is equal to 2 because we are trying to solve a spherical particle. And how about F? By rearranging the mass balance equation in order to have, you see here, the derivative of X of the multiplication of X squared, the effective diffusivity divided by the square of the radius of the particle times the first derivative of concentration within the X. Then you can just realize that F is equal to this product. So the ratio between effective diffusivity divided by the square radius of the particle and then the first diffusivity, derivative of concentration along X. About S, it is just the rate expression. So rate expression multiplied by the density of the catalyst. So you see that, of course, a work is needed, because even if you are really very well used to write down a mass balance equation for a spherical particle in a form reported in the left-hand side, you should just a bit play with mathematics and express it in a similar manner with the MATLAB syntax. So in order to then define C, F, and S. But as soon as you have it, then the implementation is rather logical and easy. I will show you an example. What about icfun and bcfun? Well, they really depends on your need. If we are considering, for example, a spherical particle that is empty of the reactants and products, it means that at time equal to 0, along each position of the catalyst particle radius, we have that concentration is 0. So it means that actually it just means that the concentration is equal to 0. So very straightforward. What it is less straightforward, but so it requires a bit of preliminary work, is to define the boundary conditions, because also in this case MATLAB provided the syntax where you must define two terms, an algebraic term that can be function of the position, time, and concentration in our case, and then another term that is Q, that can be function of X and T, that is multiplied by F. Actually, this F was already defined before, so it is the same F. And this sum is equal to 0. So we have to modify our boundary condition in order to have the same syntax. But that's rather logical, because if we are taking these two boundary conditions, so symmetry at the center of the particle, so 0 derivative, we have that the P term is equal to 0 because we don't have algebraic terms. And we have that that Q can be taken, for example, equal to 1. And in this case, because if Q is equal to 1, it means that we only have F equal to 0. But if F is equal to 0, it means that this term that we have seen before, so the ratio between the effective diffusivity and the square of the radius multiplied by the first derivative calculated at X equal to 0 is equal to 0. So you see, you have to play a bit with this kind of function, but then it can be rather easy. In the second case, if we are taking the simplest boundary condition for the concentration of each reactant at the catalyst surface, that means that this concentration is equal to the surface concentration that can be defined. It means that F is equal to 0, because if F is equal to 0, we have that the derivative terms is equal to 0. So we take Q at 0, Q times F becomes 0, and we have P equal to 0. So we just have to define P. But P is just the difference between the concentration at the catalyst surface minus the concentration within the bulk phase of the fluid. So if you take this difference, then it means that this difference is equal to 0, and then practically the two concentrations are equal. So you need to actually write down these kind of equations and obey, let's say, to MATLAB syntax in order to have a form that can be implemented. About the modeling approach, I will show you a code because, as you will see in our book, we have implemented all the codes and all the codes are present. So let's say that the balance between the theory and application, it's not really respected because we have a few theory, but a lot of application, a lot of code examples that are written there. You can copy paste them within your Matlab and execute them, and they actually works. So researchers of both industry and academic world, they can have already some tools as a starting point to develop our tailored codes. But I will show you a couple of. The first one is about this particle case. And the code was written in such a way to have different parts. The first is the definition of the simulation settings, then the definition of time and space grids, pdepe call and solution, plus the definition of the functions that are needed, and finally the output generation. I won't go really in detail about the description of each line, but I will just talk about the main sections. First section, simulation properties. We just copy paste here the values of the radius of the particle, the bulk phase concentration, kinetic constant, or whatsoever. Then we have the PDE call using the syntax I've shown you in the previous slide. So we have the solution, call of the PDPE, and then the definition of M. We took 2 for a spherical particle, and then the 3 functions that are pdepefun, icfun, and bcfun, and then the definition, the call of xmesh and tspan, that are just actually 2 vectors defined here. But what can be important is how to write each function. I just copy paste here the final form of our 3 coefficients, C, F, and S, and you can see that the syntax is rather straightforward. We just write that C is equal to epsilon, F is equal to this term, and S is equal to this other one. And of course, we need the reaction rate, and it is defined here. So you see just few lines of code. Of course, one has to know how to write them, but with few lines of code, then we are able to solve a partial differential equation problem. I have also copy paste here the boundary condition function, so bcfun and also icfun. Also in this case, they are rather logical. We have to define P and Q for both left and right extremes of the integration domain. Let's say that this is a kind of this is MATLAB syntax. Left in this case it is x equal to 0, and right in this case is x equal to 1. So as previously reported, P for x is equal to 0 is 0, while Q is equal to 1, and in this other case Q, so when x is equal to 1, Q is equal to 0 because we don't have the derivative term, while P is equal to the difference between the 2 concentrations, as previously reported. So also in this case, 4 lines of code, and then we have the boundary conditions. And about the initial condition, that's extremely rather easy. If we just want to take that concentration is equal to 0, we just say that U0 is equal to 0. So you see, it's not, let's say that the coding part, it's not the most complicated point. What it can be complicated is the derivation of each coefficient for your specific problem. Then we have the output generation. So we are back in the main script. Well, we just have created some figures using subplots, and then we have a surface here, and then a plot here. This is a parametric plot, and yeah, but what it is interesting, it is here actually the generation of the output. You can see that MATLAB correctly calculates the concentration trend along both x and time. So at the time equal to 0, we have that the concentration is equal to 0 here because this is our initial conditions. We have considered considering the particle empty. Then we have that the reactant starts to diffuse along the time and then to react. So we have a profile at long times that can be considered at steady state. So the trend is rather logical, and it is even more visible here at the right hand side of the figure when the concentration is plotted against x. at different times, and we can see that at short time we don't have reactant within the particle, so we are still in the diffusion section, so reactants are diffusing, and then of course simultaneously reacted, and then at long times we have the steady state condition. So you see, that's rather practical. The results are logical. So if somebody is facing with a problem related to the single particle simulation, then of course one can just copy paste the code and then customize it. So it is a good starting point in our opinion. Then example number 2, we have an axial dispersion model for tubular reactors. That is something very common. I don't go really deeply in the mathematical part. Just say that we are taking a dynamic into consideration a dynamic mass balance, where we have a first derivative of concentration with the time. We have convection term, axial dispersion term, and then reaction rate. Then written in dimensionless form, because we have solved the dimensionless form case, fixing a reaction rate of a first order with a reactant feed of 1 mole per cubic meter. And then here we have defined initial and boundary conditions, so a pipe that is empty of the reactant at time equal to 0 along all the reactor length, and at the entrance of the pipe we have a constant concentration and a 0 derivative at the outlet of the pipe. So rather classical. So we are talking about a case where either we have an homogeneous catalyst or an heterogeneous catalyst where the effectiveness factor is equal to 1. So no concentration gradients along the catalyst pellet. So neglecting all the it means that the algebraic term is equal to 0, p is equal to 0, while q is equal to 1, because in this way f is equal to 0. That means that the first derivative of concentration along x at x equal to 1 is equal to 0. And then we have this equality at the reactor entrance. So it means that q is equal to 0 because we don't have a derivative term, and then the algebraic term is straightforward. It's just taking this term and putting it at the left-hand side. So this difference becomes equal to 0, sorry. The pipe is empty, so u0 is equal to 0 as to fill the IC function. Also in this case, you see a rather simple and straightforward case, but the output is also in this case very well illustrative. I've reported here 2 simulation examples. The first one is no reaction, so K is equal to 0, the kinetic constant, and those are the results of the simulations imposing different Peclet numbers. So let's have a look, for example, at this one for Peclet equal to 1000, so approaching by plug-through behavior. We have that at dimensionless time of 0, the pipe is empty, and then it gets filled of the reactant within a stepwise manner, because of course we are simulating a stepwise experiment. And then if we cut these surfaces at the outlet of the reactor and we plot the concentration of our component A along x equal to 1 along the dimensionless time, we have that it is really very nice to have these sigmoidal trends that becomes different, logically different when Peclet decreases. So starting from a plug flow, ending up with either kind of non-ideal fluid dynamics. What happens if we take the reaction rate on? So if the kinetic constant is not equal to 0, then of course we have a similar trend, but at the outlet we don't have that concentration reaches the value of 1, of course, because A reacts in order to give B. And of course it is also very nice to see that a plug flow behaves better than either kind of reactors where the fluid dynamics is not really very ideal. So everything that is in line with theory, but you are able just to do that if you choose the right solver, and in this case pdepe. Okay, you have also the second option to write the routines, the discretization routines by yourself. You can do that, but we suggest when the mathematics is not fully complicated, and if you manage to write your mass balance equation within the form that MATLAB requires, then please use pdepe. It is of course easier and life is easier. Then I show you the third example. This is actually a real case of application where one of our routines was used, let's say in the past, to simulate some experiments collected in lab scale. This example is a packet bed reactor with the fluid solid mass transfer resistance. The theory is included in our book, chapter 6, and it is 1.5 pages of theory because we just write down the main mass and heat balances equations, and then we have the code example. And the experimental data were collected and published in 2007. It was dealing with the esterification of oleic acid with methanol. So very straightforward reaction using an heterogeneous catalyst. At the moment I don't remember which one, probably amber light or amber list, I don't remember. And the authors, and Professor Tesser is one of the authors, of course, and they apply two kind of models. First one is a packet bed reactor, so ideal packet bed, neglecting mass transfer resistances, rather straightforward, and they simulated the system with another kind of software, but nowadays you can use MATLAB using either OD45 or OD23 or whatsoever. And the model can be written importing the experimental data, defining chemical and physical properties of the chemical components, the reactor properties like how much catalyst is loaded within the reactor, or how much reactants is fed to the reactor itself, so calculating the input variables, calling the ODE function, and then plotting the data. What they observed is that this figure is taken from the paper, while this one is the picture that we have reproduced with MATLAB. We have that the experimental data follow a really very nice trend within the volumetric flow rate, the overall volumetric flow rate of the reactants. So by increasing the volumetric flow rate, you have a decrease in conversion of the main reactant, but the simulation is really very bad because, as you can see, we always get a straight value that is actually the chemical equilibrium value. And we get actually the same result within MATLAB. So it means that the model, the ideal packet bed reactor, cannot really describe the collected data. There is something else. What can be there, as molecules are rather big and flows are rather low, the authors assumed that very probable fluid solid external mass transfer diffusion could occur. So they decided to write down a much more complex and sophisticated model, including two main mass balances equation, one for the bulk liquid phase, so considering convection and the diffusion term, along actually the stagnant liquid film surrounding the catalyst pellet. And then we have a second equation that is a pseudo-steady state condition where diffusion is equal to reaction. So what it diffuses, it reacts on the pellet surface. So in order to implement it, the mathematics is a bit more complicated, and we will have an example. I will show you just the result of this example. You have to define, of course, the mass transfer coefficient and the catalyst specific surface per reactor volume. We had a number here that is reported for the mass transfer coefficient. The authors used the Couret correlation that is valid for packet bed reactors. The values were tabled in the manuscript, but the correlation is rather easy to be implemented because it is a classical Actually, it is a straightforward correlation where the Sherwood number is a function of Reynolds and Schmidt numbers for within certain ranges, and the fluid dynamics of the experiments felt within these regions. So by explicitating the definition of Sherwood, Reynolds, and Schmidt, it is possible to obtain directly a function where the mass transfer coefficient is like the ones it is here reported. So it's actually a function of the fluid velocity, the particle diameter, viscosity, diffusivity, so all known properties. So by implementing this correlation and the value of the specific surface area, then it was possible just to simulate experiments. So again, the strategy: import of the experimental data, definition of chemical and physical properties, thus the definition of the reactor properties, calculation of the input variables, so very similar to the previous examples. And then the main difference: we don't need to call only the ODE solver, but we also need to call the fsolve solver, because we have to solve simultaneously the algebraic equations. And finally, we have the data plot. In this way, I'm not showing the code. It can be distributed, of course. It is possible to better simulate the trend. This is not a fit, this is just a simulation. So you can see that the calculated profile follows really better the experimental trend. So again, a case that can be of interest for researchers of both the academic and industrial world. So with that, I'm over. I have completed my presentation, and I give again the word to Professor Tesser. Please.
Thank you, Vincenzo. Okay, the example 4 is dedicated to a very frequent topic in chemical reaction engineering, mainly in laboratory, that is the parameter estimation. This example is related to parameter estimation in batch reactor test. And in particular, we have considered a system of 5 components, and these 5 components are involved in a complex reaction network, in a complex reaction schemes that is reported here. For such a kind of system, we can build, first of all, the stoichiometric matrix, including in this matrix the component on each row of the matrix, for example, and the reaction on the column, organized as row and the columns. We have used this stoichiometric matrix by considering that the first reaction behind an equilibrium reversible reaction is coded as two different reactions, that is the forward and the reverse. So starting from this chemical system, chemical reaction networks, and from this stoichiometric matrix, we have developed the case in which concentration along time data for the 5 components have been collected, and we considered time ranging from 0 to 1000 seconds, and at each time we have a measure of concentration of 5 components. In this case, not really the concentration, but the number of moles. In this table of experimental data are collected all the experiment. Well, now we need two other blocks to define the simulation and the fitting, that are reaction rate equations, that are normal reaction rate equations, and the mass balance for each component that is reported here. The mass balance, obviously, behind a batch reactor is made of an accumulation terms and the reaction terms. In this mass balance appear directly the stoichiometric coefficient taken from the stoichiometric matrix. The problem is then to find the 4 rate constant K1, K2, K3, and K4 that realized the better fitting of the experimental data. So we have to match the model to the experiments. And in this case, we have to determine the 4 adjustable parameters by considering that the experiments are conducted at fixed temperature. Here, the output of the code reported in the book is presented. For example, the first as a subplot. In the first subplot, you have the time evolution of the number of moles of A, B, and C. And for each component, you can see the experimental data and the model behavior that well represent the experiments. In the second plot, you have the same type of profile in time for D and E component. But this is a very normal way to represent experimental and data fitting. In this last plot, is interesting to observe a sort of sensitivity study in which the parameters are reported in a form, in a ratio form, corresponding to 1. In correspondence to 1, you have the optimum parameter. And then you have a scaling factor, a multiplying factor, in which you can increase or decrease this parameter. From this kind of output, you can decide which parameter is more influent on your model, on the objective function of your model. In fact, you see that K1, in this particular example, K1, K2, and K3 are parameter very influencing the objective function. As when you move away, when you move far from the optimum value, the objective function increases very steeply, while the parameter K4, on the contrary, is not very very important for what concerns the objective function. But on the contrary, K4 can be the parameter less easier to be determined, because wide variation of this parameter does not involve a variation of objective function. The final output of this type of calculation is the best value of fitted parameters. You can see here we have reported the optimum value of the parameter together with the confidence interval is a statistic value associated with each parameter that represents the error connected with the parameter. And then usually these confidence intervals are reported at 95% of the probability. Another important information on obtained as output is the correlation matrix. The correlation matrix is an information in which the user can decide if some parameters are correlated with others. Normally, values of the element of correlation matrix near to 1 means that the corresponding parameters are correlated each as a couple each to another. And the best output would be to obtain, apart from diagonal, all correlation matrix elements very low, not near to 1. So this is a typical output of, as an example of fitting problems reported, example reported in the book. The last example that we show you here is an optimization. Optimization means regard a very broad topics in chemical engineering and plant design, and normally is devoted to the search of a minimum or of a maximum of function. In our example, taken directly from the book, we have simulated the optimization of an ammonia autothermal reactor operated in a way that the feed is preheated before entering to the reactor. We have a feed that reactant feed that pass in a shell, and then its temperature is increased until to reach the entrance of the reactor. The reaction occurs, and then the outlet stream is analyzed. The problem of this kind of optimization is to define a function, define the minimum or the maximum or of a function of 4 parameters. The reaction is exothermal reaction. Nitrogen is converted to ammonia, as we well know, and this catalytic bed is represented by an objective function of 4 variables: conversion, nitrogen feed, feeding temperature, and gas temperature. This function, this example was taken from the literature. This objective function was represented as the economical annual income in dollar per year, and with the opportune substitution, the objective function can be defined as here is reported. Is a sort of a polynomial function of which the maximum must be determined. The problem is that each calculation of the objective function involves the solution of 3 differential equations. So the problem, the code, must embed an equation, an ordinary differential equation solver inside a minimization solver. Here I reported the 3 mass balance and heat balance equation. The kinetics is well known. After the definition of the initial condition at the entrance of the reactor, the problem is defined as follows: search for the maximum of the objective function f subjected to some constraint. In particular, these constraints are that the temperature must be kept inside the range 400-800 Kelvin degrees, and the length of the reactor must be confined between 0 and 10 meters. In the table, I reported some other necessary parameter physical properties of the system. And by the use of a solver appeared in a very recent version of Matlab, the genetic algorithm of maximization in this case, we have obtained the following output in this case. So you have the temperature profile in which you can see the feed temperature that is preheated until you have the entrance of the reactor. From the beginning of the reactor, the temperature starts to increase until to reach a maximum behind the reaction exothermic, and then you have a decrease due to heat exchange. In correspondence, you have the consumption of nitrogen according to the reaction occurring, and this profile corresponds to the maximum of the objective function. If we want to have a pictorial view of the objective function, we can represent the value of the process in terms of dollar per years, and as a function of 2 of the variable of the system. I mean, temperature and length of the reactor. substantially, we have obtained at the end of the optimization procedure a reactor length, an optimal reactor length of 7.5 meters and around 700 degrees. In correspondence to these optimal conditions, the objective function involves an outcome of around $5 million per year. So the tools, the Matlab mathematical tools, can be used also for maximization of function. I think that I have end my talk, so we can start the question session.
Yeah.
I think.
Yeah.
And
Thank you so much, Vincenzo and Riccardo. That was a lovely talk. For all the attendees, if you have any questions, please just put it in the Q&A section and we can get to them now. As of now, there is, oh, I see some coming in. There's one question here about whether you can get a certificate for viewing this seminar, and we'll get back to that later. But for now, I'm going to focus on the questions for the speakers. So we have one in the chat. It says from Francesca. Thank you for the interesting talk. Are the simulations computationally expensive?
what do you do?
Yeah, Francesca, it really depends on the code, actually. So, for example, the first case I've shown you, the single particle case, no, not really. Within seconds, you have a simulation. And the third one, it is more expensive. But then you know that most of the time you should frame a code like that within a parameter estimation solver. This is the main point. So if you are, of course, running a parameter estimation with a code that is running that needs to run some minutes, then of course you need a certain time. So it can be time consuming, but then it also depends on the computer you are using, because MATLAB can exploit, for example, parallel computing. So within parallel computing, then it is possible to faster the computation. For instance, I'm using an octa-core with double threads here, and the most complicated system framed within a parameter estimation, for me, they last more or less 2 or 3 hours, the most complicated. Easier tasks, let's say, within the range of 5-6 minutes. So this is my personal experience.
Well, but the example reported in the book are solved within 1 minute.
Yeah,
the maximum.
Yeah, maximum. So if you just copy paste them and then you run them, yeah, because those are very, very well structured examples, and the tasks are not extremely. You don't have so many components, for example, because as many components you have, then the computation times increases. For parameter estimation, the initial tent values are already very well framed, so you're not starting from I don't know, very exotic parameters, but they are very well framed. So
yeah, and it's possible to copy and paste from the ebook the code directly.
Yeah.
So we have another question here from Ramin Maghrebi. My apologies for my pronunciation. Thank you very much for the interesting introduction of the book. What are the advantages of using MATLAB compared to Aspen Plus reaction simulations in Reactor's point of view?
Yeah,
controversial maybe, I don't know.
But well, it depends on what you have to do, because if you need to simulate a reactor and to tune up the calculations, like including intraparticle diffusion, external diffusion, include a very complex reaction rate expression, then you are forced to use a software different than Aspen Plus. So it really depends on your application. So you can simulate a reactor with Aspen, with ChemCAD or whatsoever without any kind of problems, but it really depends on what you have to do. If you have a power law expression and all the diffusion effects are negligible, then of course, please use Aspen, it's better. So you can also put in line a distillation column or whatsoever, and you draw up all the scheme. But if you are interested in the definition of the intrinsic kinetic of a system, including all the mass and transfer phenomena, you cannot use Aspen. So
are very different tools.
Yeah,
very different.
So Aspen is made for process simulation, material and energy balance, have a lot of thermodynamic model, and is very different tools with respect to MATLAB.
Yeah. So we have quite a lot of questions coming in now. I don't know if we'll get to them all, but we'll see. So the next question comes from Stilanos. Says, thank you for your very interesting and useful talk. My question is related to solving boundary value problems in catalytic reactions. What is your opinion about MATLAB solver BVP4C/5C? Is it a reliable method to calculate intraparticle diffusion? Thank you.
BVCP, the boundary value.
Okay.
We have an experience with that. It is reliable, but some of these solvers, even pdepe, they can crash or collapse depending on the geometrical nature of the problem. Because if, for example, for some way, because of the parameters or because of the chosen feed concentration, the problem is not elliptic or parabolic anymore, they collapse. They start to fluctuate, or they start to give you a warning problem or even an error. So in that case, you should then better to discretize the integration space and solve with the numerical method of lines, for example, the issue. So it really depends on the geometry of your system. Frankly speaking, we have used that in some cases. It works, and it works also very nicely compared to with the other kind of solvers and softwares.
Then we have another question here from Tia. It says, thank you for your talk and greetings from Aalto University in Finland. Does your book have examples where deactivation of the catalyst is taken into account?
No, actually not. We have not included them.
But it's very easy to include, I think.
Yeah, because most likely it is.
You can start from an example and then improve with a further equation in catalyst deactivation.
Yeah, because most likely it is an additional ordinary differential equation, sometimes a function of the reaction rate, sometimes function of other kind of parameters depending on the deactivation. So if you start from one of that example and then you add an additional ordinary differential equation, it's not complicated to do that. Yeah, not at all.
Lovely. Okay, we have another question here from Carlos Miguel. Does your book cover modeling chemical reactors in T, Z, and X? Which functions would you suggest for this, or do you think that MATLAB is not the most suited software for this purpose?
If you have discrete variables, you cannot use pdepe, so you should discretize it. So a numerical method of lines. There are also other softwares, Athena, Visual Studio, GPROMS, Model Builder, yeah, also something about console. But then it really depends on what you have to do, because at least for my experience, for a personal experience, there is no other software as such efficient in parameter estimation than MATLAB. Compared to the other ones, because then of course you can have an easier life in simulating a multivariable space with other softwares, but those softwares are a bit lacking in the parameter estimation section. Some of them, they also have the statistical included, but for example, the research of the minimum of the objective function, most likely it is, you know, a gradient-based method that it's not the most efficient one. You should run tens of parameter estimations to have the order of magnitude of the initial 10th value of the parameters. While with MATLAB, if you use a genetic algorithm or a particle swarm algorithm, then you just need to press one, maximum twice, the run button, and then you have a good result. So it really depends on what you have to do. For example, in our case, even for our research study, if we need to do a parameter estimation, most likely we use MATLAB. If we are just simulating cases, so simulating a reactor or whatsoever, then we think about also at other softwares.
Yeah. Okay, we have another
rather
question.
flexible. We use here a lot of softwares, so it depends on what we have to do.
Matlab is the most flexible.
So we have one more question here from Michelle Emanuela Fontinato. Congratulations for the book and the presentation. My question is, what determines the choice of a parameter estimation tool rather than another? Which I think is a bit related.
Yeah, thank you, Michele. Yeah, it really depends. The simplest, like LSQ non-lin, it is really very practical because the execution is rather fast, even if it is a gradient-based method, so that you have to run different parameter estimation. While if you have a lot of parameters to be estimated on a lot of experiments, so the space grid of the variables is very wide, then you should run hundreds of parameter estimations, preliminary parameter estimation tests. So in that case, it will be better suggested to use a natural-based algorithm, for example, like particle swarm or
evolutionary algorithm.
Yeah, an evolutionary. So again, it depends on the application.
Problem.
Yeah, I apologize that a lot of our answers are like that, but it really depends on the case. Yeah.
Yeah, it depends. We have another question here from Agil Safarov. My apologies also for my pronunciation to everyone. Thanks very much. Are there some examples of choices for the best reactors for some given reactions?
Within the book, you mean? No,
yeah.
No, it's not. Yeah.
I think in the book is a
comparison.
Is implied, but I'm not so sure.
Between two reactors.
Yeah. There is just the comparison. For example, we didn't put examples like optimization of different reactors fixing a kinetic rate expression. Yeah.
Perhaps in a next book. Okay, so I'm just seeing now if there's any, because I was looking mostly in the Q&A, if there's any that have slipped through in the chat, and I don't see any at the moment. Given that we're 4 minutes to 12, this might be a good time to wrap it up. If you have any additional questions, of course, you can always email the speakers. I'm sure they would be pleased to continue the discussion.
Yes, of course, of course. Please write us, and then we can keep in touch.
I believe their emails are on the EFC's website. If not, you can search their names quite easily and find them.
They're on the front cover of the book, but they're put on the Gruyter website, on our
and also on this presentation.
Yeah.
On the EFC website they are as well.
Yeah, perfect. So very readily accessible. I'm going to hand it over maybe to my colleague Karen, and she can close out the session. But thank you all so much. So
Karen? I just wanted to point out we have another question.
Oh, do we? Oh, it popped up.
Yes.
I thought I got them all.
About how many examples are there included in the book?
Sorry?
Yes, I see this from Santiago Alcantara. It says, thank you for the presentation. My question is, how many examples can I find in each chapter in the book?
Oh, we don't remember the number, but
from 5 to 10, I think.
It depends on the chapter, but
depends. It depends.
Again, it depends.
Classic answer for this session.
If you just give us a second, we can.
Yeah, and then there's also one other question from Antonio. Congratulations on the book. Are there any examples of electrochemistry in the book?
No, electrochemistry is not treated.
No,
not treated here.
Yeah, about the exam, there are some chapters with 9 or 10 examples, other with 8 examples, other 12 examples too. Yeah, so
from 5 to 10.
Yeah,
from 5 to 10 each chapter.
In each chapters.
Yeah, quite a lot. Okay, now I'm double checking that there are no questions. See them pop up accident when I'm halfway through speaking. No, okay. then I'll hand it over to Karen, and maybe you can close out the session.
So thank you, all of you, for the good talk, for the many questions at the end of it, and we hope you had an interesting time.
Yeah.
Thank you very much.
Yeah. Thank you very much to everybody for participating.
Bye-bye.
Have a nice day to everybody. Bye-bye.
Bye-bye.